In this video, we're going to describe chemical changes, chemical reactions, and how to represent chemical reactions using chemical equations. So firstly, a chemical reaction is a process where elements or compounds will interact together to form new substances entirely. So I'll show you an example of something that's not a chemical reaction and that's not a chemical change, and then we'll see an example of something that is a chemical reaction. So suppose you have water as a liquid, H2O liquid, and you heat it up so that it starts to boil and turns into a gas. What you'll notice is that when it's a gas, G here, it's still H2O. We didn't change what it was. It just changed its states. So by simply changing states, that's not really a chemical reaction or a chemical change because the water is still H2O. It still has the same chemical identity, the same chemical formula. But let's say you took water and you passed electricity through it. So much electricity that it actually broke water apart so that you got some hydrogen gas and some oxygen gas. This would be considered a chemical reaction because you actually broke chemical bonds. You actually turned the H2O into two new things, H2 and O2 separately. So you made new substances. They're not water anymore. That would be a chemical reaction. And so the way that we wrote it out here is actually a chemical equation, and we'll go into that in more detail soon. How do you know if a chemical reaction happened versus it not happening, a physical reaction? Well, you can look at some evidence of chemical change. The first is a color change. So when you mix, let's say, two colorless substances together, so substances without color, they might react and form a substance with a new color altogether. It doesn't have to be green, but the point is there's a color that's unexplained. It wasn't there before, and now it is. You could have formation of a solid, so sometimes you'll mix two solutions together or two liquids together, and a precipitate forms, little chunks of solids forms. They actually look kind of cloudy. So here you can see an example of a precipitate forming. Right here, you see a cloudy color that appears, and that's actually solid, and if you let it sit over time, it'll settle at the bottom, and you'll see it almost looks like sand at the bottom of water at the beach. You could have formation of a gas, so usually you see that as bubbling. Now, just to be clear, if you boil water, you'll see bubbling, but it's not because a reaction is happening. You really have to see bubbling when you just mix things together without changing the temperature, and all of a sudden you see bubbling. And that's because one of these new substances you made was a gas. So when you mix vinegar and baking soda together, for example, you make some carbon dioxide gas, and that's what you see the bubbling as. Sometimes you might see a change in energy. That change in energy can be seen as light being produced, like when you crack a glow stick, for example. It could also be seen as a change in temperature, which counts as a change in energy. So sometimes the container starts to feel hot where the reaction's happening because it's releasing energy, or sometimes it starts to feel cold because it's absorbing energy from its environment. You might also have an odor or taste change. Typically, you wouldn't taste things in the lab, but odor change, you could smell that pretty readily. But just an example, when milk rots, it smells different, it tastes different. That's because the new compounds that are made have a different odor and taste altogether. So you look for these clues, and if you spot these clues, that's how you know that a chemical change has likely happened. So when you have a chemical reaction happening, you need to represent it. And so the way we represent chemical reactions is using what's called a chemical equation. A chemical equation is basically a summary of what's happening in the reaction. And we usually write it in a certain way. You usually have what's called your reactants on the left side of this arrow. And then on the right side, you have your products. The reactants are essentially what you start off with. They're your ingredients. They're on the left side of the arrow. Whereas what you make, those are your products, those are on the right side of the arrow. So there's a few different types of equations you can have. You can have word equations, skeleton equations, and balanced equations. Word equations uses words only. So for example, here you can see sodium, chlorine reacting. So sodium plus chlorine are reacting. Then it says here to produce sodium chloride. So these are your reactants over here on the left side, and this is what's made on the right side. The plus basically means and. If it's on the reactant side, it could mean reacts with. The arrow means to produce or to make or produces. Then you can also have what's called a skeleton equation. So a skeleton equation, instead of showing words, it'll show symbols, formulas, and states. So the word equation from here is translated into a skeleton equation. We have Na, S means solid, so solid sodium, and Cl2, chlorine gas, react to produce NaCl, which is sodium chloride, in the solid state. So a skeleton equation is a little bit better. It gives you more details about the chemical makeup of the substances reacting and being produced. It tells you the formulas. It also tells you what state they're in. Are they solid, S, gas, G? Are they liquid, L? Sometimes we say aqueous to say if something is dissolved. So for example, if I had a beaker of water here, and I had some solid salt, solid sodium chloride, and I put it in water and stirred and dissolved, it would then become NaClAq, aqueous. Aqueous means watery, so a watery solution. It's dissolved in water. Okay, so that's AQ. You never put states in the word equation though, so don't put states in the word equation. You just put them in the skeleton equations. And then you have something called a balanced equation. We'll see that in more detail later on, but you can probably already see the difference between the two. The balanced equation has big numbers in the front to make sure the atoms are the same on both sides, and you'll learn about that in more detail later on. For this lesson in particular, we're going to focus on word equations and skeleton equations and make sure we follow the rules. So let's do an example over here. We're going to do, usually in a question that involves word equations and skeleton equations, you'll be given a description of a reaction. You're going to be asked to identify the reactants, products, and then to write a word equation and then possibly a skeleton equation. So here we have solid sodium metal and chlorine gas react to form sodium chloride. Write a word equation for this reaction. So to do that, first you have to identify what your reactants are and what your products are. There's some key words. You'll see here to form. So what is formed? Well, it's sodium chloride. So you don't have to write the state right now. You can write sodium chloride. That's a product that was made. Then what's reacting? What do you start with? Well, it says you're starting with solid sodium metal. So sodium, we just have to write the chemicals, not the states. And then chlorine. So sodium is a reactant, and so is chlorine. They're the ones reacting. So to write your word equation, we'll write the reactants first, sodium plus chlorine. We're then going to put an arrow, and then on the right side of the arrow, we're going to put the compound made, sodium chloride. Sodium chloride, like that. And that's a word equation. Now, remember, word equations, while they are useful, so here we have sodium plus chlorine producing sodium chloride. You can see they're kind of long to write. And also, not everyone speaks the same language. So sodium and chlorine and sodium chloride, they're different in different languages. So not everyone will be able to understand this word equation written in English. So that's why sometimes we'll instead write a skeleton equation where we convert everything into their symbols. Now notice in the word equation there's no states, but in the skeleton equation we will have to put states. So we're just going to translate everything that we have in a word equation to a skeleton equation. So, and we'll see if we have any state information. Usually state information is given to you in the question. If it's not, there's some key points you have to remember. So for our first one is sodium. Sodium, we'll notice it says solid. So sodium, and we can put a little S. Plus, next we have chlorine. Chlorine is a gas. Now, I need you to remember that there are some elements that are called diatomic, so Hoff, Brinkel, These elements exist in pairs. So H always exists as H2, Cl is Cl2. And you have that in your data tables. So if you go to your data tables over here, and you scroll down here, you have all the diatomic elements here. So you just have to know to look at the back of your periodic table to access the diatomic elements. So when you see one of those written alone, not in a compound, because this is a compound here, but written alone like this, chlorine, then you have to write it in its diatomic form, Cl2, and its diatomic form is gas. It even says that here. If it doesn't, you should know it's gas. Then we put our arrow, and then we're going to make the formula for sodium chloride, which is a compound. To make the formula for that compound, you just use the rules that we learned throughout the unit. If it's ionic, you crisscross. If it's molecular, you use the prefix, right? So we have Na plus 1, Cl minus 1, crisscross. You get NaCl, and it says solid here. So that is our skeleton equation. There's states, there's symbols, there's formulas, but there's no words. And again, some students get confused here. They say, why isn't there 2? I thought you said it was Hofbrinkel. I did say it was Hofbrinkel, but only if it's alone. Here it's in a compound, and you have to use the crisscross rules. So don't worry too much about the fact that you're missing a Cl. That will solve later. If you notice that, good. We'll solve that one later on. Right now it's just about writing with the rules. So I want you to pause the video, and I want you to try this one yourself right over here, and then you'll take it up by unpausing the video. So hopefully at this point you've tried it yourself and you've unpaused the video. So we have solid calcium reacts with fluorine to produce a solution of calcium fluoride. For this scenario, identify the reactants, identify the products, and write word and skeleton equations. So let's start with A. We're told that calcium reacts with fluorine. So we know that calcium is our first reactant. And then we also have fluorine. B, we're asked what's the product. There could be many products. In this case, it just says that we're producing a solution of calcium fluoride. So we have calcium fluoride as our product. Okay, C, we have to write a word equation. So for the word equation, we're just going to do calcium plus fluorine producing calcium fluoride, because it's our product on the right side of the arrow. Then we're going to do our skeleton equation. So we're told that calcium is a solid, so Ca, solid, plus fluorine, remember that's one of the Hofbrinkel ones, so Ca, so F2, and it's gas based on the diatomic rules that we learned, and also from your data table, produces calcium fluoride. So just to show you your work, it's ionic, so 2 plus, F1 minus, crisscross like that, and we get CaF2. And it says a solution. Solution means it's dissolved, so we put aqueous as our to indicate our state. So solid, gas, and then aqueous over here. And so this would be our skeleton equation for this particular reaction. Notice again, there's no states in the word equation up here, and there are states in the skeleton equation over here. We identified our reactants and our products, and that's essential in any of these reactions. So in this video, we saw how to pay attention to the evidence of chemical changes. We saw different types of chemical equations to use to represent chemical reactions. Those equations were word equations, skeleton equation, balance equations. We focused on word equations and skeleton equations in this lesson. Your practice problems are on the following few pages. There will be a video lesson to accompany it, but you can also take a look at your answer keys over here when you're doing these problems. A few other things is sometimes to remember states, it can be difficult. For diatomic elements, just when they're not in the compound, these are the ones you have to remember here, right? Gas, 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 and then finally bromine liquid and iodine solid. We didn't learn about acids yet, but when you do, acids and most bases and solutions are going to be aqueous. Metals, for the most part, are solid except for mercury. It's a liquid metal at room temperature. Noble gases that make sense, they're gases, and anything else that's not in this little list here will be specified in terms of states. And you'll get the hang of it. The more practice you do, the more you realize, okay, a metal is usually solid unless it's stated otherwise. It'll make sense to you as you do more and more practice. So attempt these problems here and then check your answers. There'll be a video lesson for you to check your answers as well